So today we'll be doing partial fractions decomposition. The materials that you will need are a notebook and a pen or a pencil. So for our warm-up, solve the following integral of x minus 2 cubed over x to the fourth minus 4 dx. Take some time to talk. Okay, so since we already know how we would solve this, I'm going to run through it kind of quickly. So if you're just working with this integrand and you're trying to reduce the integrand, you would end up with x squared minus 4x plus 4 over x plus 2. And after using synthetic division, you would have x minus 6 plus 16 over x plus 2. And then to solve the actual integral, put that back under the integral. The integral of x minus 6 plus 16 over x plus 2 dx. And that would give you 1 half x squared minus 6x plus 16 and absolute value of x plus 2 plus 8. So this is how we know how to solve the integral of a complex fraction, but there is a much easier way to use methods that we've learned before instead of just reducing like this. We can use partial fractions. So partial fractions is a theorem that says that every rational function, no matter how complicated, comes from adding similar fractions. This helps us evaluate the integrals using techniques we've already learned. Our goal today is to be able to express a rational function f of x as the sum of a polynomial for fractions with linear factor denominations and fractions with denominators containing quadratic expressions. So there are a few rules when writing a rational function for f of x over g of x as a sum of partial fractions. The first rule is that the degree of the numerator f of x must be less than g of x, which is the denominator, and if it's not, we have to divide and work with the remainder. And then also we must know the factors of g of x. So the general steps are, so the first one is to factor the denominator completely. Write the denominator in terms of linear factors or quadratic factors, which can also be repeated. Separate the fractions where the sum is the original fraction. Assign variables like a, b, or c to the numerator of the separated fractions. Multiply both sides by the factor denominator to get rid of the fraction. Group the terms and by the power of x. Equate the coefficients of like terms on both sides of the equation. And then find the variables. And there are two methods. One method is plugging in x, plugging in a number of x that would leave you with one variable left to work with. But today we're going to be doing the second method, which is solving with the systems of equations. So our first example is 5x minus 3 over x squared minus 2x plus 3. So first, we would reduce this, or factor the denominator, to have 5x minus 3 over x plus 1, x minus 3. This should be a minus. Okay, minus 2x minus 3, not plus 3. Okay, so now we assign the variable. So we do a over x plus 1 plus b over x minus 3. And next we have to multiply by the denominators. So we're multiplying by this whole thing on both sides. So it would leave you, on the left, you would have 5x minus 3 since it cancels out. And then on the right, you would have a times x minus 3 plus b times x plus 1. And after distributing, or multiplying out, you have ax minus 3a plus bx plus b. So now we have to group these in terms of x. So you still have 5x minus 3 on the left, and then x, and it's ax plus bx here, so it would be a plus b. You're just grouping them and then factoring out the x when possible, plus negative 3a plus b. And now we equate the like terms on both sides of the equation. So 5x equals x times a plus b. The x's would cancel, and you would have 5 equals a plus b. And then you have negative 3 equals negative 3a plus b. Okay. And the next step is to solve the system of equations to get a and b. So I would multiply this first equation by 3 to cancel out the a and solve for b. So you would, when you multiply this by 3, you would have 15 equals 3a plus 3b. And then you add the second equation, so it's just negative 3. And this one stays the same, so negative 3 equals negative 3a plus b. And when you add that, you have 12. This cancels. 12 equals 4b. And you have b equals 3. Okay. And then you have b equals 3, so you just plug that in to one of the other equations. So I'll plug it into the 5 equals a plus b. So 5 equals a plus, and b is 3, so a plus 3. When you solve, you get a to be 2. So the partial fraction of 5x minus 3 over x squared minus 2x minus 3 is 2 over x plus 1 plus 3 over x minus 3. Okay. The next example, 6x minus 22 over 2x squared plus... Okay, actually, no, sorry. Before I go on to the next example, I wanted to actually have some notes that we go a different color. So A and B here, these are what are called undetermined coefficients. And then the whole fraction, the fraction of b over x minus 3 and the fraction of a over x plus 1, those are the partial fractions. Okay. So this example, 6x minus 22 over 2x squared plus 7x minus 15. Take a second to pause if you want to solve it on your own. So again we reduce or factor the denominator. So 6x minus 22 over 2x minus 3 and x plus 5 times x plus 5. Now we have to separate it and assign letters or variables. So you have a over 2x minus 3 plus b over x plus 5. And after multiplying by the denominator, on the left you have 6x minus 22 equals a times x plus 5 plus b times 2x minus 3. That would give you 6x minus 22 equals ax plus 5a plus 2bx minus 3b. So now let's group them in terms of x. 6x minus 22 equals x times a plus 2b plus 5a minus 3b. Okay, so now we have to equate them to the like terms. So 6x equals x times a plus 2b. The x's would cancel. 6 equals a plus 2b. And then negative 22 equals 5a minus 3b. Okay. Sorry. All right, so I'm going to multiply this top equation by -5 to cancel out the a in the bottom. So you would have -30 equals -5a minus 10b. And then the bottom will stay the same. Negative 22 equals 5a minus 3b. Add them together. Negative 52 equals negative 13b because the a's cancel out. And then, so when you divide 13, the negative 13, the b is equal to 4. And then we can just plug it back in. So 6 equals a plus 2 times 4. 2 times 4 is 8. 6 minus 8 is 2, so, or negative 2. So a equals negative 2. So we would end up, so the partial fractions of 6x minus 22 over 2x squared plus 7x minus 15 would end up being negative 2 over 2x minus 3 plus 4 over x plus 5. Okay. This example uses repeated linear factors, so the denominator is x minus 2 squared. So you don't have to, obviously you don't have to factor the denominator, it's x minus 2, x minus 2, but it's only a little bit different. It's generally the same steps, just a little different with the denominator. So you still do a over x minus 2, but when you're doing the next one, you keep the square. So it would be b over x minus 2 squared. So I still have to multiply by the denominator to cancel them out. So on the left, I'd have 7x minus 11 equals a times x minus 2 squared plus b in the x minus 2, oh wait, no. A times x minus 2, because it has them. It has an x minus 2 here, so only one of them cancels. And then the b stays the same. Because, or, no, sorry, it's just b, because the x minus 2 squared cancels. So, after distributing 7x minus 11, ax minus 2a plus b, and you don't really need, they're kind of already grouped, ax plus negative 2a plus b. So we can just use 7x, oh, sorry, they're kind of connected. 7x minus 11 equals, oh my god, sorry, 7x equals ax, and then the x's will cancel, so 7 equals x. And then negative 11 equals negative 2a plus b. So we already know 7 is a, so we can just, or a is 7, so we can just plug that in. So negative 11 equals negative 2 times 7 plus b. Negative 2 times 7 is negative 14. Add the 14 over. B equals 3. So the partial fractions of 7x minus 11 over x minus 2 squared would end up being 7 over x minus 2 plus 3 over x minus 2 squared. Okay. And okay, our next problem, the partial fractions of, or find the partial fractions of 3x squared minus 24x plus 53 and x cubed minus 6x squared minus 9x. Or instead, it's solve using the method of partial fractions. So here you would factor out an x in the denominator. So you have 3x squared minus 24x plus 53 over x, and then x squared minus 6x minus 9. Okay, so assigning the variables, it would be a over x plus b over x minus 3. Oh, sorry. When you factor the, when you factor this, it's x minus 3 squared. So the denominator is really x times x minus 3 squared. So it's plus, so a over x plus b over x minus 3, but then it's plus c over x minus 3 squared. And then you have to multiply by the denominator. So on the left, you'd have 3x squared minus 24x plus 53 equals a times x minus 3 squared plus b times x and x minus 3 plus cx. Okay. 3x squared minus 24x plus 53 equals ax squared minus 6ax plus 9a plus bx squared minus, oh, that was bx squared minus 3bx plus cx. So now let's group in terms of x. Okay, this is always going to be right. So equals x squared times a plus b plus x times negative 6a minus 3b plus c plus 9a. And when we equate on the like terms, so 3x squared equals x squared times a plus b, so 3, the x squared would cancel, 3 equals a plus b. Negative 24x equals x times negative 6a minus 3b plus c. The x's would cancel. Negative 24 equals negative 6a minus 3b plus c. And then 53 equals 9a. There's no other variable for it. So 53 equals 9a. So a equals 53 over 9. And since we know that, we can plug it into the first equation. We can plug it into the first equation. 3 equals a plus b. So 3, because we need to have the same denominator, just multiply by 9. 3 is 27 over 9. So 27 over 9 equals 53 over 9 plus b. And after subtracting over, b is equal to negative 26 over 9. Okay, and then I'm going to box that so it's more clear because there's kind of a lot on the screen. And then you plug that in to our negative 24 equals negative 6a minus 3b plus c to solve for c. So you'd have negative 24 equals negative 6 times 53 over 9 minus 3 times negative 26 over 9 plus c. Okay. All right. So when we multiply the negative 24 by 9 and then by 9 over 9. Yeah. So you have negative 216 over 9 equals, this would be negative 318 over 9 plus 78 over 9 plus c. And after putting that all together, or moving everything over, you would have c equals 24 over 9. So for the partial fractions of 3x squared minus 24x plus 53 over x cubed minus 6x squared minus 9x would end up being 1/9, because you could factor out a 1/9. 1/9 times 53 over x minus 26 over x minus 3 plus 24 over x minus 3 squared. Okay, and then the last example is this one. It has irreducible quadratic factors. Okay, yeah, so you can't reduce the x squared minus 2x plus 5. So we have to do, okay, so you have a over x minus 2. You still have to assign the variables, but for the x squared minus 2x plus 5, when you're, because remember that the numerator has to be at it has to have a smaller power than the denominator. So if the denominator has x squared, the numerator has to have an x in it. So it would be bx, and then you have to include a plus c over x squared minus 2x plus 5. Okay. After multiplying by the
denominators to get rid of the fractions. We have 6x squared plus 21x plus oh, I'm sorry, that was the wrong. You would have, let's see, okay. You would have 3x squared minus 7x plus 12 equals a times x squared minus 2x plus 5 plus bx plus c times x minus 2. Okay. So ax squared, so 3x squared minus 7x plus 12 equals ax squared minus 2ax plus 5a plus bx squared minus 2bx plus cx minus 2c. That's a little messy. It's okay. And now we can group these into x squared times a plus c plus x times fa, or 5a, I keep saying f, fa plus b plus 5b plus 3c. Put that as parentheses. Okay, and now I have to equate the like terms. So 3x squared equals x squared. 3x squared equals x squared times a plus c. The x squared would cancel. 3 equals a plus c. Negative 7x equals x times 5a plus b. The x's cancel, so it'd be negative 7 equals 5a plus b. And then finally 12 equals 5b plus 3c. Sorry, that can be c. Okay. So let's see. Let's multiply the 3a plus b times, oh, wait, I messed up here. It's not a plus c, it's a plus b. That was a mistake. A plus b. So this is also a plus b. So 3 equals a plus b. Multiply that by 10. So, okay. So 30 equals 10a plus 10b. And then multiply negative 7. I think I made a mistake. I did make a mistake. Okay. This is all wrong. I was looking at the wrong. So it would be x. Sorry, guys. X times negative 2a minus 2b plus c from c. And then plus a plus 5a minus 2c. So let's rewrite these. Because I messed it up. Okay, so it would be negative 7 equals negative 2a minus 2b plus c, and 12 equals 5a minus 2c. Sorry about the mistake. Okay, so we multiplied the first one by 10. We're going to multiply the second one by 5. So we have negative 35 equals negative 10a minus 10b plus 5c. And then let's solve that. So negative 5 equals, these will cancel, equal 5c. C equals negative 1. Okay. Now we know c, so let's plug into 12. Okay. We'll see. Wait, I need to solve for b now. So 3 equals a plus b. Or no, I'll solve for a now. Okay, yeah, so I solve for a. So 12 over here, 12 equals 5a minus 2 times negative 1. That is 12 equals 5a plus 2. Subtract 2. 10 equals 5a. And then we have a equals 2. And then finally, we can plug that in to our last equation. So negative 7 equals negative 2 times 2 minus 2b. And then it was plus c, so it would be minus 1. So negative 7 equals negative 4 minus 1, so negative 5 minus 2b. Add the 5. Negative 2 equals negative 2b. B equals 1. So, let's go to the top. After working all that out, you would end up with 2 over x minus 2 plus, remember the b is 1, but you still have the x. So it's x minus 1 over x squared minus 2x plus 5. Okay. So that's all I have. The homework is on textbook pages 646 and 647. And it's just questions 1 to 6. So, yeah.
Length of curves, also known as arc length. Length of curves is determining the length of a continuous function y equals f of x on a closed interval a to b. The length of a curve can be calculated by approximating the curve with straight line segments. So these line segments of n, you create an infinite amount of them until they get smaller and smaller to create that curve to calculate the value. We assume the derivative is continuous when looking at the graph. So we can draw the graphs. To estimate the length of the curve, we again divide the interval into n subintervals and then integrate these segments. As we infinitely create these line segments, the length of each line segment decreases, causing their combined length to be the most accurate value of the curve. This concept is very similar to finding the area of a solid or the volume of a solid by stacking up disks or washers an infinite amount until it's a solid shape and you find the volume, or by the area creating trapezoids. In this case, we're just creating line segments. This concept is shown by L equals the limit as n approaches infinity, the sum from 1 to n, the absolute value of p sub I minus 1 p, and pi is the point at each end of the line segments. So this is the formula for arc length that you need to know. Very important, start in your books. It is L equals integral of ds. There's 2 different ds's. One is in terms of dx and one is in terms of dy. So this is how you determine which one you use when you find your formula. If it's in terms of x, you use the first one. And if it's in terms of y, you use the second one. Note that no limits of integration are put on the integral, as the limits will depend on the df's that we are using. So basically, the integral that you have, whatever it is in terms of, and whatever df you will be using will determine the limits of integration that you are using. If your function is in terms of x and your integral is in terms of x, that's simple. You just use that integral. But if your function is in terms of y and your interval is in terms of x, you may have to do a little subbing and change it to get your limits of integration. These are some steps to think about when you're solving them, and then we'll go through an example together. Given a function and an interval, determine which formula you will need to use and find that derivative. You plug in the derivative to the formula. You can simplify the root now or later in the integral, and then set up the formula in the integral. You determine the limits of integration based on your interval and what you are integrating with respect to, and then you solve the integration. Don't forget the trig identities and use sum. Sum is very important and is used a lot when solving more complex equations. And finally,
So keeping those steps in mind, we're going to solve this example. Determine the length of y equals ln secant x between 0 less than or equal to x less than or equal to pi over 4. So first we want to see what it's in respect. So this is going to be with respect. I'm going to use a better color. With respect to x. And your interval is also with respect to x. That's very simple. You're going to use the first ds equation, which is, again, the roots of 1 plus dy over dx squared dx. So first off, you want to find the derivative. This is the step you always want to take first when solving or trying to figure out the length of the curve. So you find the derivative. Derivative of secant is secant x tan x. And since it's ln, you multiply that by 1 over the inside, which is secant. These cancel out. The derivative is tan x. When we take this and plug it back into this equation, we get ds equals square root of 1 plus, cut the derivative, tan x squared dx. Now, this is back when I said the steps. You can either simplify the root or put it into the integral. So you can right now just put the integral in and then do substitution. But what I'm going to do is simplify the root. So we have 1 plus tan x squared. That is a trig identity, if you remember. So this will become ds equal to the square root of secant squared x as identity. And since secant, well, this is squared, so this becomes secant x absolute value. Because the secant x is in the integral, you can take away the absolute value, and it's just going to be secant x. So now this is what you're going to put into your integral. So now we have L is equal to integral secant x dx. The limits of integration in respect to x, so they're going to be 0, pi over 4. And now you just solve. You guys know how to do integrals. So this is going to be ln absolute value of secant x plus tan x from 0 to pi over 4. Plug those values in. And in the end, after you solve it out, you will get ln rad 2 plus 1. So that is how you solve for the curve length. Sometimes you're going to need a calculator to determine the actual value, or you can leave it as something like this. You don't have to do the calculation, but this is the basics of how to solve. Here's another question. Example 2. Determine the length of f of x equals 1 plus 6x raised to 3 halves between 0 less than or equal to x less than or equal to 1. Pause the video and try to solve it on your own. And then I will solve it with you. So, like we did before, this is in terms of x, and this is also in terms of x. So, we need to use the first dx. Do it again. 1 plus y over dx squared dx. The derivative of our function is the first thing we find. I'm going to simply put this into my integral. Again, you can plug it in, solve the root, but you can also just start off immediately doing this. 9 x squared x, and our interval is our one step first, 0 to 1. This, once we simplify, 0 to 1, 1 plus 81x. And here's where the use of comes in. It will be very helpful to know use of very well, because length of curves uses it all the time. So, we're going to do it here. We're going to have u equal 1 plus 81x. Our du will be 81x. Take away the 1, because there's no equal equation, and we get dx. Now we need new limits, of course, so we have 0 plus 81 times 0, which equals 1. Equals 1 equals 1 plus 81 times 0 equals 82. Now that we have that information, we are going to make our new integral. Our integral 1 over 81 from 1 to 81 or 82, sorry, grad u du 1 over 81 times 2/3 u to the 3 times. That is the antiderivative of rad u from 1 to 82. And then solve, simplify these. 2. You multiply these, so you can just figure out the u a little easier. 2 over 2. 82 minus 1. This is again where I said before. It gets a little tricky trying to multiply it out, so you can either write it as this. Or plug it into your calculator, if you're allowed, to get 6.103. And this is the length of your curve. So that is again an example of how to do it using u substitution. This next one, I want to show you that it's very helpful to determine what you're in respect to when solving your problem, because it just makes it easier, but you are able to solve without using the original with respect. So first I'm just going to show you this is in respect with y, and so is this. So we are going to use the second ds, which will be 1 plus the x over dy squared dy. So in doing this, your derivative will be y minus 1 to 1/2. Basically, rho y minus 1. I think in this case, it's pretty easy to plug it into your roots because it simplifies nice and simple. So I'm going to plug it in to get 1 plus rad y minus 1 squared, and that is 1 plus y minus 1. Very simple. These cancel out, and you're going to be left with rad y. You plug this into your interval from 1 to 4 because your interval is for the limits for your integration. Change the element, rad y dy, and then that's a very simple one to solve. with respect to the original equation, but you can take it with respect to the other equation, and that's what I'm going to show you. This is with respect to y. I'm going to show you how to take it with respect to x. I'm going to write down what x is again, just so we can see. And then integral. It's a little messy, but there we go. So, first things first, when you take it with respect to a different equation, you want to change your equation so it's perspective for what you want. So we need this to be in terms of x, but right now it's in terms of y. So we multiplied 3 over, divided 2, and we raised 2/3 out of 1. That's basically how you do it. You know how to solve equations. But you will end up with a new equation of y equals 3x over 2, where 3 halves times x, to the 2/3 plus 1. Your derivative for that, dy over dx, because now it's in terms of x, so you can use that equation, is 3x over 2, the negative 1/3. Now, we'll talk about your limits in a second, but we're going to solve for the roots. You have dx equal to 1 plus 1 over 3x, the 1/3. Since it's a negative 1/3, I just brought the fraction, put a 1 over it so I don't have to worry about that negative. It gets a little complicated. This is why you're going to see it's easier to just find what the respect is, because it gets a little much. Plus 1, and then 3x over 2. You just want to combine. And then you get simplify it. So this is now what you're going to put in your integral. It's a lot. That's not something you want to be solving, but you can't solve it. L what we just solved. 3x 2 Oh, I missed a step, guys. Just realized this needs to be squared. So this will become a 2. That's a 1. And this also needs to be 2. Everybody makes mistakes. But this is a good reminder. You have to square this derivative or else your formula, you're going to see it's totally different. Don't forget to square it. There we go. Okay, that's true. Now, we don't know what our limits of integration are because they're right now in terms of y. So what we do to solve that is, I'm going to do this over here. We plug in these values of y into the original equation. So we're going to have x of 1, that's our first one, into the original equation. Our first limit of integration will be 0. Our second one will be 4, because this other interval as it now is 4. So we plug that into the original equation. This is some number with a decimal, so we can just simplify it for now. 2/3 times 3/2, and that's what I'm going to use as my top limit of integration. It's a little much, but it'll be easier to see than to write like a decimal. So now we have our limits of integration and our f of x dx. Again, you will need to use substitution because there is no way you'll be able to solve this on your own. U equals 3x over 2 to the 2/3 plus 1. It's our inside function, and we know that if we use this and we get derivative, it will help us out. Because you will see, by taking a derivative, will get us 3x over 2 to the negative 1/3 dx, which is right here. So, now we have to do new limits of integration after finding all that, but it's just what we have to do. U of 0 equals U of 0 times U over 2 2/3 plus 1 is 1. U of 2/3 plus 1. U of 2/3 times 3/2 equals, it equals 4. Don't want to have to plug that all in. So now we have another new equation. L is equal to 1 to 4 rad u du. That looks familiar. That looks like this equation right here. So now we solve that again. And what we'll see, 2/3 u to the 3/2 from 1 to 4 will give you 14/3. The exact same answer as what we did before. But as you can see, it is a lot of steps, a lot of thinking, and way more work than you have to do. But sometimes you may get asked to find a curve that's not respected to, so I want you to know that it is possible. But if you're doing it on your own, look at what the equation is and just solve with respect because it's so much easier than all the work we just had to do. Some key takeaways I just want you guys to remember. The formulas. You need to know the formulas. Even I just forgot one. You have to remember this has to be squared because that affects your whole calculation if you mess that up. You have to know when to solve the function with respect. X or y, we just did that. You can do both, but it's easier to pay attention to what the function is and what the interval is. Know how to choose the limits of integration using the information given, just like what I said. If you need to plug in a x to find new limits, you know how to do that. And understand and use the simplified root. So how to use them. Yes, we simplified the root for the last question, but still needed use of. We have to determine whether or not you need to do more because sometimes it will be a more complex function. But you guys know how to simplify and do use of, so sometimes you just gotta put that together. So besides the homework that you will be doing at the end, I will give you a little worksheet and you have a few questions to solve about the length of curves.
Hello, this is Dervin. So right now we'll just quickly go over improper integrals. Proper integrals, it's not really a hard concept. It's kind of similar to taking a basic definite integral, except with, some just new techniques. So first, our goal is to evaluate an integral whose limit is infinite, or where the function is unbounded, where it would be discontinuous. Determine if an integral is converging and diverging. This is the materials you'll need. So first, this is our warm-up. Pretty basic integral. Find the area under the curve x from 3 to 8. Pause if you need some time to work on this. Pretty easy. So you just take the antiderivative, x squared over 2, and plug in, and you'll get 55 over 2. In the decimal form, it will be 27.5. It's pretty easy. This is the second part of the warm-up. Another basic integral, 1 over x. We're going to be taking the finding the area under the curve from 1 to e. Pause if you need some time. 3, 2, 1. So you just take the antiderivative, which is ln x. So you plug in ln e minus ln 1. And you'll get 1 since ln 1 is 0 and ln e equals 1. Now let's refer back to that warm-up. As you can see in part A, we found that the value of the integral of x is in the closed interval. But with improper integrals, we're pretty much going to be taking the same interval, but over the open interval. Meaning we're not taking like the entire value, we're like taking it as it approaches like from either the left or the right. The warm-up questions are considered definite integrals, which are functions that are continuous on closed intervals. But an integral that has like limits of infinity or is being integrated on the open interval are all considered improper integrals. We can evaluate these problems through the ideas of limits, as we'll see in our further examples. First, let's note when evaluating an improper integral, if you get the solution, if the solution is a real number, then the integral will converge, and if the solution goes to infinity or isn't a real number, you'll know it's divergent. You need to memorize that. These are some tips to help. We'll look at the p-series, which is pretty much looking at the degree of the denominator. So as one can see, if you eventually keep practicing, you'll notice a trend. When the degree of the denominator is greater than 1, then you're most likely going to get a real number, which means it's going to be convergent. And if it's less than or equal to 1, then it's going to be divergent. We're not going to go into this too much into detail, but you'll see as we look at in further examples, and you can notice this trend on your own. So now these are examples of improper integrals. For the integral from 0 to 3, it's improper because if you plug in 3, it's going to be undefined since you can't have a 0 in the denominator. Same thing for 1 over x, 0 is going to be undefined. And if you plug in infinity, you'll get not a real number, so that's an improper integral. So now I'm going to be showing you ways to solve improper integrals. So if f is continuous on a to infinity on the open interval, then you'll take the limit and plug in, sub in b for infinity, which will be the integral from a to b. You solve that, get that antiderivative, and plug in. Same goes for if f is continuous on negative infinity to b. You'll take the limit, sub in a to find the antiderivative, then you'll plug back in later. For 3 to 4, instead of infinity, you're going to be plugging in real numbers. And you'll usually see this when the value makes it discontinuous, or you're going to just be approaching either from the left only or from the right. So that's why it's best to take a limit as you integrate it so you can this is the first example. See if you could solve this. We're going to be solving on the open interval first. If you notice, this is the same as the warm-up. Instead, we're going to be approaching 8 only from the left. So first, you find the antiderivative of the integrand. Then you just substitute the endpoints of the limit of integration. Then you take the limit, plug in b for a. Since it's on the open interval, we're only conserved as we approach it from the left. So you take that antiderivative, you get b squared over 2 minus 9 over 2. Then you just plug back in a for b. And same answer, 27.5. So since it's a real number, as we take this integral, well, you notice it converges. Now this is another example. We're going to be solving integrals with infinity and undefined. This usually happens a lot, quite often, which could be sometimes confusing when it becomes undefined, but the same concept applies. So first we're finding the area under the curve of 1 over x. See if you could solve that. Give you a moment of pause. 3, 2, 1. So you're going to be taking the antiderivative. Then you take the limit as a approaches 0 from the right, not the left, since the open interval, it's the lower limit of the integral. As you take the limit, you take the antiderivative, you just plug it back in later, and you'll notice that you get an answer as infinity. And as we looked at previously, if you evaluate it and the number's not real, then that means it diverges, which is important to know. Difference between converging and diverging. Now we'll look at solving integrals with interior infinity. So you'll notice if f becomes infinite at an interior point c of the interval of integration a to b, then improper integral is expressed as a sum of two improper integrals. It's usually like this when there's discontinuity, especially like infinite discontinuity when it's both like pointing up. So this will be the equation from a to c, then you add that from c to b. And note, only if you evaluate and the solutions are both real numbers, then it's going to be converging. If one of them are not a real number, then it's going to be diverging. This is our last example. This is an example of finding the area of the curve. If you notice, there's going to be discontinuity at an interior point, which is going to be 1. So you're going to have to take the limit as you approach 1 from the left and the right and add those limits of integration. So pretty much split it apart. You take the integral from 0 to 1 since it's going to be discontinuous at 1. Then you take the integral from 1 to 3. You take the limit as b approaches 1 from the left for here, and as a approaches 1 from the right on here. Take the antiderivative. Get that 3 times x minus 1 to the 1/3. Then you plug in b for here and a for here. As you plug in, it's pretty simple from there. Then you just plug back in 1 later on. And as you realize, you'll get the answer is 3 plus 3 times 2 to the 1/3. And as you see, it is clearly converging since it's a real number. So for homework, we're pretty much going to be practicing the same as questions. The pages will be 658 to 659. Numbers 3, 5, 11, 13, 15, 19, 41, and 43. Most of them, you'll be wondering if it's converging or diverging, and the other ones you'll have to solve by showing your work. But if you notice, for some of them, a lot of them you don't have to like solve out fully. If you just take a look at the p series and the degree, you'll notice if it's converging already or diverging, which is a nice little strategy to save time. And keep in mind for 43, it's a little trick. You're going to be taking integration by parts not once, but actually twice, which they'll try to trick you here. And if you need the solutions, you could copy and paste here. You copy and paste, click the link, and you'll get the answer. It's right here. These are the solutions for the homework.